In this video, we continue our conversation about linear model evaluation, specifically model performance. Once again, this topic falls into the regression subset of supervised learning algorithms and focuses on the evaluation aspect, specifically trying to assess the performance of the model. In this video, we aim to begin to answer questions like, is the model accurate? And does it predict new observations well? The data we'll be using throughout this video show the engine displacement versus the miles per gallon, MPG, for 2018 vehicles originally obtained from the EPA and further cleaned and made publicly available by Julia Silge. The model output is shown on the right. One way we can measure variation in a variable is the total sum of squares, or SST for short. It is calculated as the sum of the squared differences between the actual response values, the yi's, and the mean response value, y bar. These differences are indicated for a few observations in the graph on the left in blue. The SST is about 25,922. The second plot indicates some residuals in red. Summing all the squared residuals gives us the residual sum of squares, RSS for short. This tells us the amount of variation still left in the response variable after accounting for the explanatory variable. So, RSS divided by SST is the proportion of variation in the response that is left unexplained, which means 1 minus RSS over SST is the proportion of variation in the response explained by the model. That is the definition of R squared. For this model, the R squared is about 0.525. R squared is always between 0 and 1. Values closer to 1 indicate a stronger model. So, let's use R squared to evaluate model performance. Right? Well, as it turns out, R squared is not the greatest statistic to use to measure model performance. In the model shown here, I have added 2 garbage variables to the model. By garbage, I mean that each variable contains random numbers from a standard normal distribution. You can think of them as noise variables. From the model output, we can see that after accounting for all other variables in the model, none of the garbage variables is statistically significant. But we also see that the R squared has increased from the model with no garbage variables. And this will always be the case. R squared will always increase with the addition of more explanatory variables, even if they are completely useless. Adjusted R squared is an improvement of the R squared statistic. If we have n observations and p is the number of explanatory variables in the model, the formula for adjusted R squared is defined as in the equation at the top. When there are no predictors, this is exactly equal to R squared. Otherwise, it will be less than R squared. You can take time on your own to prove that mathematically if you'd like. The part inside square brackets on the right side of the equation has 2 competing pieces. Where the 1 minus R squared piece decreases as the number of predictors increase, the fraction n minus 1 over n minus p minus 1 increases. In order for the entire piece inside square brackets to increase, thus increasing adjusted R squared, the R squared has to increase a large enough amount to overpower the n minus 1 over n minus p minus 1 fraction. In the 2 models we examined, we see that even though R squared increases, adjusted R squared decreases when the garbage variables are added to the model. Although this statistic is better than ordinary R squared. Both of these are dependent on the variation in the response variable. It can be easier to explain a larger portion of the variation in response variables that are highly variable. And even if a lot of variation is explained, the results may still not be very accurate, meaning predictions could still be expected to be quite far off from their actual values. That leads us to our next statistic, root mean squared error. The formula for the root mean squared error, RMSE for short, is shown here. It is the square root of the average sum of the squared residuals. In practice, this quantity tells us approximately the average distance between the actual and predicted values, or, on average, how far off a prediction will be. The R code for how to compute this by hand is also shown. Later, we will learn some functions that compute this for us. The RMSE means that, on average, the predicted MPG will be about 3.92 miles per gallon off the actual MPG. So, it seems like we have a good measure of model performance or accuracy now, right? Let's look at another example. In the plot above, we see the relationship between displacement and miles per gallon for a small sample of 10 observations. We have also colored the points by drive. Then we fit a model using 5 explanatory variables. The model output is shown in the table. We see that the p-values are all very close to 0, so close that they have been rounded to 0. The adjusted R squared is 1, and the RMSE is virtually 0. It seems that this is an excellent model, right? As it turns out, maybe not. We will discuss more in class where both of these statistics, RMSE and adjusted R squared, have failed us and how we might go about fixing the problem. Try to think of some ideas before the next class on your own.